Hello, my name is Elena Noltenius. Today I will be presenting Lab 19, Electric Field and Potential Experiment 1 for Physics II Laboratory. So, an intro to this experiment, we're going to use a multimeter to detect and draw equipotential lines in a variety of configurations by mapping electric potentials. Specifically, we used two types of configurations. We used the dipole configuration and the parallel plate configuration. So here in the screen you can see some of the materials used. There's a picture of them here, and they're listed out here. So we used aluminum foils, two alligator clips, two AA batteries, a double A battery holder, a 250 milliliter beaker, a digital multimeter, a field map, well, or three field map printouts, a petri dish, Play-Doh, a ruler, scissors, one transfer pipette, a printer, two different color utensils, two paper sheets, water, and a willing participant to record or be on the watch. And here's me with with all the materials used. So in these next few videos, you'll see the experimental setup for the experiment using both the dipole and the parallel plates configuration. So here I have my experimental setup. I have already turned the multimeter to the 20 mark, as you can see, and then I have already filled my beaker to the 50 milliliter volume as instructed, and I'm now putting a thin layer of water using my pipette to transfer the water, and then put a thin layer over the base of the petri dish, as so. So here I have my video number 2. Now, as you can see, I have already connected one of the alligator clips to the positive side of the battery holder, all the way to the left aluminum foil rod, and then I'm connecting the negative side of the battery holder to the right aluminum foil rod, like this, like that. Now, as you can see, next video. So now I'm putting the red probe, the black probe in contact with the right sphere, like this. And then the red probe in contact with the left sphere, like this. And I'm observing as the reading is changing. It's going up in the multimeter. Next video. This is the parallel plate configuration.
Yeah.
Okay, so right now I'm holding both the black probe and the red probe to the right rectangle and left rectangle, and the multimeter is changing a lot, but I would say it looks like it went up to 2. Right now it's lower, but if we leave the black probe on the right rectangle and move the red one along the field map, you can see how it reaches 2 if I put it near the left rectangle. But once I move the red probe to the right, the voltage starts to decrease. As seen, it starts decreasing. So that's how I can get my equipotentials. Yeah.
Yeah.
So for our results and tables, specifically for the dipole configuration, the voltage decreased by steps of 0.5 volts when moving the black probe from the positive dipole to the negative dipole. On the other hand, for the parallel plates configuration, the voltage decreased by steps of 38, 0.38 volts. On these maps, the characteristic dipole pattern is illustrated by the curvature of the equipotential lines in the dipole configuration. The equipotential lines are uniformly spaced and perpendicular to the plates, to the parallel plates configuration, which suggests a uniform electric field. In the end, the predicted shapes of electric fields were validated by the equipotential lines, which exhibited distinctive patterns dependent on the electrode positioning in the custom configuration.